Okay, so here in 10.3, we now need to start determining how good of a fit these curves are, and also when we make these lines, when we make an analysis, we make a prediction of an estimate. We also have to recognize that you know um, the line's not perfect, and so we want to determine how much of that imperfection is something that we can live with, and how much of it is something that we might struggle with. There are a couple of different ways a couple other measures that are associated with correlation and regression. Specifically, we're going to talk about the coefficient of determination, okay, the standard error of the estimate, and the prediction interval. We really won't do a lot with the prediction interval, but it kind of gives us a window to say, hey, you know what? You could say what you think y is. If you plug 4 in for x, what's y? But really, the prediction interval gives you a window around that y to say, look, we're really confident, we're 95% confident that the correct y is between these two numbers. So it gives you a little bit more wiggle room when you're presenting that data. But we're going to live with a standard error estimate and the coefficient of determination most of the time. First off, the coefficient of determination is the ratio of the explained variation to the total variation. The symbol that we use is r squared. Now, if you were doing the calculations in your calculator before and you noticed that there was an r squared and an r value, that's because the r squared literally is r squared, and it is what's called the coefficient of determination. And so another way to talk about this is that, say if r is 0.84, r squared is 0.7056. That's saying that about 71% of the variation or the flexibility around that answer is based on the variation in the independent variable. So essentially we're saying, hey, look, if you know the correct input, the correct x value, and you know that that's valid, 70% of the time, 71% of the time, we're going to get the exact right answer. We don't see the equation is built correctly for 71% of the movement that the x produces. Obviously, if the x has some variation in it, there's going to be some error in our y values. And so, but 71% of it's covered. But that also means that 29% of the variation, it doesn't come from the independent variable. It comes from something else. Okay? So when we talk about variation, the total variation is basically what we expect minus the actual, squared. And it's the sum of the squares of the vertical distances each point is from the mean. That y bar would be our sample mean. So each point, let me see if I can show you this picture. Okay. This right here from y prime to the y bar, this distance is what we consider explained variation. Like, we expect it to vary from average. Okay? So that's the total variation. It is the sum of those, of each distance from the mean squared. The reason it has to be squared is because we don't want positives and negatives to cancel each other out. The total variation can be divided into two parts. Or say that is way up here. Sorry. Down. That's our total variation. The unexplained part, total variation, that which is attributed to the relationship of x and y, and that which is due to chance. The variation obtained from the relationship, from the predicted y prime, is y prime minus y bar squared, and the sum of that is the explained variation. The variation due to chance, found by y bar, or y prime minus y. So there's the y bar, which is our average, to y prime, but then if there's other variation away from that, that's unexplained variation. That variation cannot be attributed to the relationships. So essentially what we're saying is that we expect it to be here. We're expecting the point to be there. And so that means that we totally understand and expect this gap. This gap exists because of variation in the x values. However, if the dot lands further away from x bar, if it lands further away than the y prime was predicting, That's unexplained variation, something we didn't expect or didn't predict. Now, if I did a scatter plot, each point has a variation that we don't understand or explain. Okay. The standard error of the estimate, also known as ZEST or CEST, okay, S estimate, okay, is the standard deviation of the observed y values about the predicted y prime values. The formula for the standard error of estimate is one of these two. We do prefer this one down here, and this is the one we're going to focus on. But this would be each y minus the expected y squared, sum those, divided by n minus 2 and a square root to remove the square. What we're going to do, okay, is we're going to do the second version of this formula. Now, you're not going to want to do this formula by hand completely, but we are going to use it, okay? We are going to use it as we go through this next process, but we'll use our calculator to help us out a lot. A researcher collects the following data and determines that there is a significant relationship between the age of a copy machine and its monthly maintenance costs. The regression equation is y prime equals 55.57 plus 8.13x. Find the standard error of the estimate. So up here, we have our formula, and we want to be able to use that. Now, we can use our calculator to help us with some of this information, but let's go ahead and write a few things down that show up in this formula. Now, what you might do is you might write like this. This is essentially what you're wanting to write down, is this sequence of numbers. So we're going to kind of try to hover back and forth here. Remember, it's a plus bx, so my a value is 55.57, and the b is 8.13, if I remember that right. Yep. And so now I need to calculate these specific values, the sum of the y's. That's my y values. I need to know the sum of the y squareds, and I need to know the sum of the x times the y's. So what I'm going to do to make my life a little easier, because I'm going to have to do so many different sums, I'm going to go to my stat, I'm going to edit in L1, I'm going to go ahead and type in my 2, 3, 4, 4, 6. Okay. And then L2, I'm going to go ahead and put in my y values. So I've got my x followed by my y, which is 62, 78, 70, 90, 93, and 103. Okay. Now over here, I need to do, let's say, an L3. Okay, I need y squared. So I'm going to take L2 and I'm going to square it. So that gives me L2 squared. Those are my y squareds. And I also need x times y. So in L4, I'm going to do L1 times L2. Now I don't want to use L3, just L1 times L2. Okay. So now these are useful numbers here. One way, I need to sum all of these. One way to sum these, okay, is to go through and just add them up with another calculator. Another option is to run the stat. I could go stat, calc, one variable statistics. If I did, I don't really want x, I want L2 here for my y's. I could calculate, and the sum will be right there, 496. But that is L2, which was my y's, so 496. Another way to do it, though, is to go to stat, and I don't see it here, so maybe I go back. Let's go here. If I go to the catalog, there might be a shortcut for this. I'll go catalog, and then I go to S. I can get to sum. Maybe I should have gone to T and gone backwards. That's a good guess. Let's go to T and go backwards. But if I did sum, and then I did L3, which is y squared, it's 42186. The nice thing about doing it this way is I can actually just come back up and switch it to L4, which would be x times y, which is 1778. And now if I use that formula that you can't see right now, the S estimate is the square root of, it starts with the sum of the y squareds, which would be 42186 minus A, which is 55.57 times the sum of the y's, which is 496, minus B, 8.13 times the sum of the xy, x times y, which would be 1778, and that's all divided by n minus 2. There were how many data values? Was that 6? So 6 minus 2. And if I evaluate this, now when you evaluate this kind of thing, you want to be careful to make sure that you're typing it in without any mistakes. I'll do this once with you, but if I really want to get fancy here, I'm going to go stacked fraction inside of the square root, 42186 minus 55.57 times 496 minus 8.13 times 1778, and then I'm going to come down and type 4. You could type the 6 minus 2, but either way you should get 6.48, and this is the standard deviation, right? It's the, I'll come back up here and let's redefine what it is. It is a standard error estimate, okay? It is the standard deviation of the observed y values about the predicted y prime. Essentially, we're saying how far off are these guys from what we would expect. And we're saying that they're off by about 6.48. Okay, $6.48 off from what we would have predicted on average. Okay, the last thing is the prediction interval. You use the S estimate, the standard error can be used, okay, to construct a confidence interval about the y prime. This is essentially, it's a t-test, you can see that, and then there's an S estimate. We can throw all of these numbers in, and there's ways to do this with technology. We're not going to do that in this class, but there is a way to build a bubble around what we expect the actual y value to be. Because we know that these are estimates, so what if we actually found the correct value, or we at least said, hey, we're 98% confident that it's between these two numbers. And so we can use that as a process to help us. All right, good luck, guys. We will see you in class.